thank you so much for giving these opportunities. And yeah, I'm happy to be back here. Actually, I was kind of summer student program in 2017 under INON. Yeah. Anyway, the topics I'm going to present today is the specially resolved evidence of inside-out coincidence in the spiderweb protocluster. In the first day, Koyama-san and Maruyama-san, they already discussed about some parts of the spiderweb, but yeah. So I will go very brief in introductions. I think we have lots of introductions in the first 1-2 days. We know that galaxy evolution is marked by we have transition from star forming to the quiescent states, and in order to get quiescent, so we have lots of things happening, and there are also physical mechanisms which drive this quenching. Is incompletely understood. Kind of question how galaxy quench from is it inside or outside in, and what is it because of the internal or external quenching mechanism like environment or ASIAA feedback or stellar feedbacks. Yeah, there are lots of things which we are not completely understood. And yes, lots of work has been done. I mean, we have lots of protoclusters and clusters, and there is a very nice plot from Shimakawa-san. We have from redshift about 3 we have this growing phase of the it's from it's kind of growing phase, and at the redshift around 2 to 3 we have the maturing phase of the around cosmic noon, and after cosmic afternoon we have declining phase where we have more starting having the quiescent galaxies, and at the higher redshift we have most of the cluster we have star forming galaxies. And yeah, there are lots of study because of this kind of reasons. And but so what I want to say is that high redshift galaxy clusters, they provide kind of ideal laboratory where we see this kind of accelerated evolutions. Also, we have multiple galaxies at various evolutionary phases where we have starting star forming and also some of the quants, and we have diverse Mars and environment. So yes, spiderweb protoclusters, I think is one of the most famous protoclusters, and lots of work has been done, as you see, lots of work has been done, and so this protocluster is kind of ideal system for investigating quenching, where we have both star forming and also the quiescent galaxies, and the dark epoch is very at the kind of cosmic noon, and it's also we have lots of extensive data from radio to X-ray. And yeah, so this is from NOFA era 2024, where using the as we see here, we have quiescent galaxies around around the centers, and we have lots of other ISL 5 meters, and also yeah. Anyway, for our multi-event data, what we did is that we used from the NOFA era 2024, where they kind of classify quiescent galaxies on the star forming using the ICST increasing data using D4000s. Greg and please for more, please check this paper. And we also have the very rich data where we have ICST and ASIAA WFC, also the JWST NIRCam, where we have lots of filters like 115, 182, 1410. And so we have, what I'm trying to say is that in this, we have lots of good data sets, and we try to understand how the galaxy quench of this. Yeah. So for this, what we did is that, as I said, we have ICST and JWST. So what we did is that we tried to do the pixel by pixel SED fitting, where firstly this is the brick methodology where we first measure the pixel scan matching, also BSF homogenization, and we cut out and we do the binning. So for binning, there are lots of ways. So we use the advanced adaptive binning from Aduro et al. 2021, and we also tried the Laborano binning just for checkout. And once we do the binning, then we do the SED fitting. For this work, I used the Seagull SED fitting, and I also tried the dense basis, and we started back pipes in the future just to check consistency all in the SED code. Then with all this, we get lots of parameters like mass, SFRS, yeah. So this is just one example where this is RGB mesh, and this is and you can see nice like mass map, also the SFR maps. Yeah, so here is the one of the interesting reason where partly we have saw the stellar mass surface density profile. So we segregate the mass into the two profiles, but this means that for we have the star-forming galaxies are mostly in the low mass, and the Poisson galaxies are in the high mass range. So about 10 to 1.5. And as we see here, Poisson galaxies exhibit steeper mass profile, and they start forming like slow, flatter profile, and also the higher central mass concentration compared to the star-forming galaxies. And so here, this is the interesting reasons how we want to see how the sequence. So we showing that, as we can see here, for the star-forming galaxies, from this is the radial profile, and we see that there is quite flat, and even inside and outside the galaxies. But for the Poisson galaxies on high mass, we can see very clear trend that. So here is the very low star forming at the around inside the center of the galaxies, but at the outskirts we have still forming stars. So yeah, so Poisson galaxies very pronounced radial gradients, and start forming like relatively flat, and this shows a clear signature of the inside-out quenching mechanism, where inside-out is like it's already quenched starting and inside. And this is just one example where we do the UBZ, and as we can see here, this is from galactocentric distance, and you can see here inside around they are falling in the Poisson regions, and those at the outskirts they are at the star-forming region. This is just one example. Then we also try to see the SFR and mass surface density map, and here we try to see with the with the morphology, where we try to segregate into we measure the size with the curve, and we here we segregate into 0 to 2, 2 to 4, 4 to 10, and you can see here most of the low star sequence. This is the forming star at the ski galaxies. They are slope is positive, and we have the transition phase and the high searching index, which is Gauss dominated. We have negative slope, and so we can see clearly is that even with the morphology also, this also depends on the Poisson galaxies, but it sends the local star forming phases with the morphology. Then we also try to see how is the star forming within the within 1 kpc scale, which is just inside the center, and we color code that with the mass, and so this is searching index, and this is SSFR within 1 kpc, where we can see very nice anti-correlation between the searching index and the central SSFR, where high searching index, those galaxies the Gauss dominated, they have very low SSFR star forming, but those don't have not most, very low searching index, they have the high star forming. So it demonstrates fundamental connection between the structural evolution and also the quenching. Yes, so here we try to interpret the physical, and so this is what we see is the pair side-out quenching mechanism, and I think the main roles will be the ASIAN feedbacks as a primary driver, and we found that out of this 11, we have 11 Poisson galaxies, so out of that around half of them are ASIAN signature, and so the ASIAN is one of the main parameter, which is quench at the starting at the center and spreading to the outskirts. And it's also consistent with other simulations from Nelson et al., which shows the inside-out quenching mechanism. Also, the morphology and also is taking as a complementary process, where we see the burst dominated are having the low star forming and outskirt region, and for the lower searching we have even flat star forming at the center and the outskirt. So, and also environment, I will not go with the deep, but because this is the a very high acceleration, so it may enhance quenching fraction in this protocluster compared to the field, and also we have other rapid gas deflation time scale and the rapid feedback process. and it's also consistent like from inside-out quenching in massive galaxies and also the simulations. Anyway, so here is the summary where we use the spatially resolved analysis with the spider protocluster, and we see this inside-out quenching and also the like it also structure and evolutions. And this protocluster spider webs appear to accelerate this process. But the question is, so here the question is whether is it happening in this or the protocluster, or is it involved all the same way, or is just for it's specific to the just the same question we discussed like past 2 days about it depends on the dynamic. I mean how active or mature the protocluster or cluster. So it will be interesting to see in various protocluster. We are just studying one case study, but in the future what we plan to do is to study the different protocluster or clusters at different redshift and also the field galaxies. So that is my that's what I'm planning to do in the field galaxies, and we have lots of data from Cosmos Web and others. Yeah. That's all. Thank you so much.
Questions?
Yeah. My question is that if it's inside-out quenching, should we also see some suppressed star formation rate, specific star formation rate in the centers of the star forming galaxy, as well as they are also maybe in the process of starting quenching? And secondly, how much of these specific star formation rate radial profile of the quiescent galaxies can be affected by post-quenching mechanisms like accretion or minor mergers?
Okay, thank you so much for the questions. So your first question is the kind of transition phase, right?
Yes.
Yeah. So as kind of saying here, we have some question, star forming galaxies with the high mass, and I think they are in the kind of transition phase, but they also show kind of similar phase with the quiescent galaxies. So I think, even though it is for massive galaxies, even though they are star forming, which is transition, they kind of showing the same signature as the quiescent galaxies. That's the first question. And your second question is like after you mean because of the minor merger or something, it's effects, right? Well, I think because once when the galaxy merges, I think it will be like after the minor merger or after star burst, it will show the kind of this kind of process. I think So then we can see here, even though the relatively strong or not, but I think they started kind of showing this inside-out quenching, but at some extent maybe not as exactly like the fully quenched, but I think it's worthy to study more details.
I was just wondering about the minimum stellar mass you can reach. I think it's 10.5 on the plot, or is there? Can you go to lower mass? And what is the completeness of your sample as well? Because if you look at the mass, it might also affect the type, the fraction of quenching, and the type of quenching you're probing.
Yes, that's a very good question. But yes, so the thing is that we, as you see here, one thing is that we don't have very high mass. We are missing kind of high mass star-forming galaxies because one of the main reason is because the ICST, because we are selecting with this prism data and it's a bit shallow. And another is our field of study is kind of very limited to because we have JWST, the size is kind of bit limited. So I think we are missing some of the galaxies star forming, and we plan to extend more deeper data. And for the stellar mass, we consider around above 9, which is kind of mass completeness above 9. Like this is from 9 to 10.5 and above 10.5 to 11. But yes, we are not complete mass sample, so we plan to do more deeper in the future.
Similar question, but are you finding that there are no quiescent galaxies below 10 to the 10.5 solar masses as well? And then is that a lack of completeness with your photometry? Because I don't think, do you have any photometry that covers H alpha at that redshift?
Yes, I mean, you mean for the question, galaxy?
Yeah, because so one thing is I don't see any quiescent galaxies for the lower mass bin, and
Only
then
one,
also. Oh, is there one?
Only one, yeah.
Oh, okay.
But it's so clearly inside out. Yeah, this one. But it's only one, so I just put the product for galaxies. But there is one quiescent galaxies around 10.1 something.
Okay. Thank you.